Hi, my name is Rich Neapolitan. I'll be covering the next 2 weeks of this course, which concern logic and probability. These slides are all based on my textbook, Contemporary Artificial Intelligence, and I've made the relevant chapters to you available on Blackboard. So your first reference should be those chapters. If you want additional references for the material, I've included some other PowerPoint presentations created by Andrew Moore from Carnegie Mellon, and he's also in charge of Google in Pittsburgh now. And I've also included some references that you can read. All right, first I'll cover logic. When we talk about logic in artificial intelligence or informatics or machine learning, we don't really mean the formal logic you'll learn in a philosophy course. We mean applications of logic in these domains. The application that I'll be talking about is knowledge-based systems. A knowledge-based system consists of the following: a data set called a knowledge that contains knowledge about the domain of interest, and an inference engine that processes the knowledge. The two are separate. The data set is the knowledge, the inference engine is a program. Often knowledge-based systems are expert systems, which are systems that make the judgment or decisions of an expert. A system that performs medical diagnosis is a medical expert system. People don't use the term expert systems as much as they once did. It was very popular around 1990. In fact, I called my first book on Bayesian networks Probabilistic Reasoning in Expert Systems because I like the term. I still like it, but it's not as popular anymore. You might more often hear these systems called decision support systems. Like a medical expert system is a medical decision support system. Here's an example of an expert system. Suppose a botanist is trying to identify a plant based on information supplied to her by her colleague, but she can't see the plant. He's on the internet giving her information. Because she can't see it, she has to ask her colleague questions to obtain the facts she needs to identify this particular plant. Plants are classified according to type, class, and family. She wants to ascertain the family. Within a type, there are many classes, and within a class, there are many families. Here is a portion of a decision tree for plant classification. 4 types are at the top. Within each type, there are classes. These dotted lines mean something follows, so I'm just not showing it. So within the type tree, there's 2 classes, angiosperm and gymnosperm. Again, dotted lines mean things follow. Within gymnosperms, there are 3 families: cypress, pine, and bald cypress. So there's a whole bunch of these rectangles at the bottom, one for each plant family. She wants to determine which one is the correct one, which one is the right family. Well, one way to do this would be to start with each family and talk about its characteristics and see if they're true or not. In other words, she could ask her colleague, is the stem woody? If her colleague says yes, then she says, is the position upright? If her colleague says yes, then she says, is there one main trunk? If her colleague says no, she knows that cypress is not the family. So she goes on to see if maybe it's pine. So she says, is the stem woody? His colleague says yes, because the colleague said yes before. Is the position upright? The colleague said yes, because the colleague said yes before. Is there one main trunk? The colleague says no, because the colleague said no before. And you can see what's going on here, all right? She's asking the same questions over and over and over again because the same attributes pertain to all the different families. So there's a much better way for her to do this. It's called a decision tree. And you ask questions that narrow down type first. All right, so in other words, you start out by saying, is the stem woody or green? If the person answers green, you know the type is herb, and then you ask questions that narrow down herb. Let's say the person says it's woody. Well, now we know then, we never ask that question again. Now we narrow down, is the position upright or creeping? If the person says upright, then you ask about the trunk. Is there one main trunk? Now see, now the answer to that question will tell us what the type is. If the answer is no, we know it's a shrub. If the answer is yes, we know it's a tree. So see, now we've concluded that the type is tree. And we can start asking questions that narrow down the class. Are the leaves broad and flat? If the person says yes, then we conclude that the class is gymnosperm. All right, now that there's supposed to be a yes and a no here, I realize, but they're kind of missing. All right, so now the person asks, is the leaf shape needle-like or scale-like? If the answer is scale-like, we're done. We concluded the family is cypress. Needle-like, is the pattern random or two even lines? If the person answers random, you say the family is pine. Two even lines. You have another question, is there a silvery band? If the answer is yes, it's a pine. If the answer is no, it's a bald cypress. So this way you go down the decision tree answering questions until you get to the bottom and conclude the family. This is much, much more efficient than the way I previously showed you. There's a problem with decision trees, not the decision tree itself, but the problem is creating them and maintaining them. Expert systems are often developed by eliciting information or knowledge from an expert. It might be difficult for a botanist to identify the entire decision tree from the top down. Even if you were an expert in this domain, could you really figure out which questions to ask first, which ones to ask second? Second, even if the botanist was able to do this, if a mistake were made, and information be added or deleted, and thus would break the edges in the tree and add new ones, the tree would be kind of difficult to maintain as new information came in. So the tree would need to be reconstructed each time necessary to change the knowledge in the system. In other words, a decision tree hard codes knowledge. It goes against this whole concept I mentioned earlier about knowledge support systems where the knowledge and the means of processing the knowledge are held separate. Now it seems that experts, rather than having a decision tree organized in their brain, they've knowledge locally organized among closely connected attributes. For example, the botanist might know that anything that has a woody stem, stands upright, and has one trunk is a tree. I mean, I even know that. I'm not a botanist. Well, I know it because I taught this material before, for one thing. But that is something reasonable to ask of the botanist rather than to create a decision tree. We can express this knowledge with an if-then rule. If stem is woody and position is upright and there is one main trunk, then the type is tree. The preceding is an item of knowledge expressed as an if-then rule. And as I said before, it's usually easier for a knowledge engineer, which is what we call the expert, to elicit localized rules such as this from an expert. Our botanists might also know that all trees that have broad and flat leaves are gymnosperms. So there's a rule like that. If the type is a tree and the leaves are broad and flat, then we know the class is a gymnosperm. Gymnosperms are like your Christmas trees. All right, so, and that's also an if-then rule that we might be able to elicit from the botanist. Here's 10 rules that we could elicit from a botanist. It's called a knowledge base. It includes the 2 rules I just showed you and other ones also. If the type is tree and broad and flat is no, class is gymnosperm. If the stem is green, then the type is herb. If, let's look at something that includes the family. If the class is gymnosperm and the leaf shape is needle-like and the pattern is 2 even lines and the silvery band is no, then the family is bald cypress. Actually, these 10 rules contain all the knowledge that is in that decision tree. In other words, I can create that decision tree. There was a partial decision tree, but I can create that decision tree from these rules, and I can create these rules from that decision tree. Now, what is the difference between the two? The decision tree gives us a way to start at the top and go to the bottom and tell us what the family is. The set of rules doesn't enable us to do that. It's just a bunch of rules. The 10 rules contain all the knowledge in the decision tree we presented, as I noted. However, the knowledge base is simply a collection of separate items of knowledge. It does not entail any particular way for using this knowledge. A mechanism that exploits the knowledge to solve a problem is called an inference engine. So once we create this knowledge base, we now need a program, an inference engine, to process it. In the next session, I'm going to talk about two well-known inference engines for rule-based expert systems, backward chaining and forward chaining. Backward chaining is the one which will take this knowledge base, as we just saw it, and essentially create that decision tree on the fly. But this will be the next